Hey guys, sorry I cannot be here today. I wanted to make sure that you guys didn't lose a day of instruction. I know you're very excited about that. We are going to continue our journey with describing relationships between two variables. We're still in Unit 1. We're in Chapter 3 where we're now looking at the relationship between two quantitative variables, and today we're actually going to start modeling those relationships with regression equations. You guys have done this before in Algebra 1 when you were doing lines of best fit. I'm actually going to show you where the math comes from and why it works. Yay! So our objectives for today, we are going to be able to interpret the slope and the y-intercept of a least squares regression line. And again, a least squares regression line is just a line of best fit. And like I said, that's something you guys did in Algebra 1. Some of you did it in Algebra 2 as well. And you've interpreted slopes and y-intercepts before. That's not going to be anything new. We're going to be able to use a regression line to predict y values for given x values. You guys can do that. That's something that you did in Algebra 1 and everything, actually, in all your math classes. You can plug in a value for x into any equation and determine the value of y. We're going to be able to explain the concept of least squares. I'll understand where that term even comes from. And then we're going to be able to determine an equation of a least squares regression line using a variety of methods. Specifically, I'm going to show you how to do it by hand. Again, I know you're so thrilled. Okay, first of all, let's understand what a regression line is. It's a linear, obviously linear relationships between two quantitative variables are going to be very common. They're also easy to understand. It's really obvious if something's a straight line. It's a little less obvious which function you would use to model a curve. But if it's a straight line relationship, there's only one function that we would use, and that's a linear model. So a regression line essentially summarizes the relationship between two variables, but it's only going to work in settings where one of the variables helps to explain or predict the other. So to fill in your little chart, so we've got a regression line is a line that describes how a response variable y changes as an explanatory variable x changes. We often want to use a regression line to predict the value of y for a given value of x. I mean, that's usually the purpose for modeling. We want to be able to make sense of a situation and make predictions from it. Regression, though, unlike correlation, requires that we have the explanatory response relationship. I mean, if we want to use it to make predictions, then we need to know that one variable is explaining the other. And so you're not going to use it necessarily in situations where you don't have that association. And again, the least squares regression line, that's the same as our line of best fit, is a model for the data. Okay, so for example, different people might draw different lines when they look at a scatter plot. So I'm just going to go ahead and draw a line on the scatter plot that I think that looks good to me. I feel like that is a good line. You may pick a different line. Now, obviously, if we're just eyeballing it, we're going to pick different lines. The one that is best is going to be the one that is closest to the actual values. And the way that we measure the closeness to the actual values is by looking at the vertical distance between the points and the line. So each of these blue dots we know is an actual value. And I'm really going to focus on the y values. So for example, this blue dot gives me an actual y value. If I look at the vertical distance, so here's my regression line. Now my board isn't calibrated perfectly, so I apologize that that's not perfectly below it. The point on my line is the predicted y value. That's what my equation would predict. Okay, and that I would have the same situation between the next point. So that would be the predicted y value for the next point, the predicted value for the third point. And so if I look at the vertical distance between the actual value and my predicted value, the goal of regression is to find a line that minimizes those red vertical lines. I want to make them as short as possible. And notice that in the term itself, least squares regression line. If you remember when we were calculating standard deviation, remember how we found the deviation between the actual values and the mean? And then we squared those values, those differences, to get rid of the negative. We're going to do the same thing when it comes to regression. We're going to square these vertical distances. And so what I'll do is I'll actually just express that geometrically with a square. And some of the squares are going to be bigger than others. And the goal of regression is to minimize the sum of the areas of those squares. So the line of best fit And the best fitting line will minimize the sum of the areas of those squares. Okay, so the actual line of best fit is going to make the area of those squares the smallest. And that's what we're going to do today. I'll show you how it's done. So to calculate the equation of the least squares regression line, we are going to use all of the summary statistics for both variables. So again, the regression line is a model for the data, much like a density curve was the model for a single variable. And remember, if it was bell-shaped and symmetric, we could determine whether or not a normal density curve was appropriate to use as a model for our data. We're going to do the same thing with two variables. We're going to start off looking at linear relationships, and then we'll look at some relationships that have a curve. The equation of the regression line is basically just going to give us a compact mathematical description of what this model tells us about the relationship between our response variable and our explanatory variable. So given that we have data on x and y for n individuals, what we're going to do is we're going to calculate the summary statistics. So we're going to actually calculate the mean and the standard deviation of both variables. And using the techniques that we learned in our last class, we're also going to determine the correlation coefficient R. And then we're going to be able to use all those values to come up with the regression line. And notice the form of the equation that our textbook uses, and this is actually the same form that the AP course uses. You're used to y equals mx plus b. Okay, so notice that the order of the variables are a little bit different in this course. Please don't get tangled up in the actual letter. So notice that in our course, we're allowing b to be our slope, and you're used to calling it m. And the y-intercept in the equation corresponds to what you typically have always referred to as b. Again, please don't get tangled up in the a and the b. Remember that the slope is simply the ratio of our standard deviation in y over the standard deviation in x, that's what the s sub y over s sub x means, times our correlation. So if it helps just to write out the formula in words, I'm basically going to take my correlation coefficient, and notice that we're multiplying it by the standard deviation of y over x. It's just like with the slope where you have the change in y over the change in x. Well, standard deviation is a measure of change. It's a measure of variation. So that's consistent with what you did in Algebra 1. So I'm going to take my standard deviation of y, and I'm going to divide it by the standard deviation in x. Okay, now remember, your standard deviations are always positive. So how do you get a negative slope? That's where the correlation coefficient comes in. So you're going to take your standard deviations, and you're going to divide them, and then you're going to multiply by the correlation coefficient, which gives you the strength and direction of your association. To find your y-intercept, well, think about solving your equation from Algebra 1 for b. If I were to solve for the y-intercept, I'd have that b is equal to y minus mx. Okay, well, that's the same as what we're going to do in this formula. My y-intercept is simply going to be my y value, some point on my line, some point xy, I'm going to use that value in my slope to determine the y-intercept. Well, it turns out that on every line of best fit is the point x bar, y bar. So the mean of x and the mean of y as an ordered pair will fall on every regression line. And so we're essentially just going to take our mean of y and subtract the slope times the mean of x, and that's how you find your y-intercept. So let's go through that. Okay, let me actually, before I do that, let's just kind of reiterate what the slope and the y-intercept represent. The least squares regression line, again, notice that we use this symbol on top of the y. There's like a little caret. That is called y hat. And we use the symbol to indicate that it is simply a prediction. Everything we're doing with our model is simply going to provide us with a prediction. If I don't include the hat there, then it is implying that the equation that I've come up with is a perfect fit and it hits all the lines or hits all the points. So you want to make sure that you use appropriate notation and put that little hat on top of the y to indicate that it is just a model. It is just a prediction. It is not actual. And so again, y, red y hat, is just the predicted value of the response variable y for a given value of the explanatory variable x. B is the slope, and again, don't get hung up with which is A and which is B. Just remember your slope, that's your rate of change. It's the amount by which your variable of y is predicted to change as x increases by 1 unit. And x always increases by 1 unit, and your slope gives you how y is predicted to change. So it's either going to be predicted to increase or decrease based on the sign. Your y-intercept then is just going to be the predicted value of y when x is 0. It's your initial value. It's what we expect the initial value to be based on our line. And I will say that students often lose credit on the AP exam when they don't specify that the slope and y-intercept are predicted values or estimated or expected values, not the values that were actually observed. So be careful of your notation. You will be asked to interpret the slope and y-intercept, so it's really important that you indicate that when in your interpretation that these are just predicted values. Okay, we're going to take a look at an example. We've got the lengths of 2 bones and 5 fossil specimens from the extinct beast. I'm not even going to try to pronounce it. This is data that we had last class. We've already looked at this data before. If I go into my stat, I think I've already got the data in there. Okay, so I've got the data in my list. I'm going to go ahead and make sure my scatter plot is set up. And it is, so I'm going to go ahead and zoom 9. And so we've seen the scatter plot before. So I know that this is my femur, this is my humerus. Okay, so I know just by looking at the graph that there is a strong positive linear association between the length of the femurus and the femur and the humerus. And I can basically tell that as the femur bone increases, that the humerus bone is going to increase consistently. So to determine the correlation coefficient R, this is the process that we went through last class. What I'm actually going to do is jump down to letter C for a second because we're asked to also find the mean and standard deviation of both of the bones. And because I want to make sure that we're not going to get any rounding errors, I want to be sure that we're storing the values in different variables. So I'm going to create a little table here where I have my mean and my standard deviation. And we're going to have to calculate the mean and standard deviation of both the femur and the humerus. Okay, and so if I go back to my home screen, I'm going to go ahead and calculate the mean of my femur. And I'm going to store that in letter A. Okay, well that's an easy one to write. So 58.2 is the mean of my femur, and I'm right next to it, I'm just going to write that I've stored it in letter A so I don't forget where my numbers are. Then I'm going to find the standard deviation. Second list, go over to math, and then option 7 is my standard deviation. And again, I'm going to do that for list 1. And this time I'm going to store in letter B. Okay, and so my standard deviation is 13.198. And I'm storing that in letter B. I'm going to do the same thing for my humerus. If you prefer, you can use the second enter button to recall previous commands. Sometimes it's a little bit easier than going back and finding the command. And then I just need to adjust that to list 2. And I'm going to save my mean. What letter am I on? Letter C. So I'm going to save that in letter C. Well, that was easy. So 66. And I stored that in letter C. It'd probably be easier for me just to type 66 than to call that up. And then I want to calculate my standard deviation. So again, I'm going to use the second enter to recall my previous command so I don't have to look for it. I'm just going to replace my list 1 with list 2. And I'm going to store the standard deviation in letter D. Okay. And so 15.89. And I'm storing that in letter D. Okay, so I'm now going to use these values to calculate my correlation coefficient. So if I go back into my lists, I know I've got my X's in list 1, my Y's in list 2. In list 3, that's where I want to put my standardized X values. So I'm not even going to bother deleting this. If I can just simply enter, to standardize it, I basically want to take X minus the mean of X and then divide by the standard deviation. So all my X's are in list 1, and I'm going to subtract the mean. So you can either use the letter A or actually just enter in 58.2. I don't need to worry about rounding there because that was exact. And then I want to divide by the standard deviation. So instead of rounding that value, this is where I'm actually going to use the value that I stored in letter B. Okay, so those are all my standardized values for X. In list 4, I want to enter in all the standardized values for Y. So now I want to take all my Y values minus the mean and divide by the standard deviation. So in parentheses, all my Y values are in list 2. I want to subtract the mean of list 2, which we already know is 66, and then I want to divide by the standard deviation of list 2, which I stored in letter D. So if I hit, if I hit alpha D and press enter, I'll get all of my standard deviations. Or I'm sorry, all my standardized values. All right, so now I have my standard values of X, my standardized values of Y. To calculate the correlation coefficient, I'm basically taking the average of the product of those values. So if I go to the tip top of list 5, I want to multiply list 3 times list 4. And I think the value shouldn't change because I had already done this. Okay, so in list 5 now I have the product of all of my standardized values. So if I go to my home screen, the next thing I want to do is take the sum of list 5 and then divide it by n minus 1. So the sum, I go to second stat, it's a math, it's under the math menu, and sum is option 5. So I'm actually going to take the sum of list 5 and I want to divide that by n minus 1. So I've got 1, 2, 3, 4, 5 data points, and so I'm going to divide by n minus 1, which would be, 4. Okay, and when I press enter, that gives me my correlation coefficient. So R equals 0.994. And what I'm going to want to do here is also store this value in a variable because I'm going to need it to find the slope, and I don't want to round. So I'm going to go ahead and just hit store, and then I'm going to store this in letter, let's see where letter E is where I'm going to store this. Okay, that's done for me. All right, so let me just write the letter E next to it. I'm going to need to recalibrate my board. Okay, hopefully this will work now. So my R value we said is 0.994, and I stored that in letter E. So the next step is to calculate the slope in the y-intercept. So my slope, if you remember from the formula before, is going to be my correlation coefficient times the standard deviation of y over the standard deviation of x. Okay, and it's always going to be y over x, and that's a big mistake. One of the things that I notice that students do is they get their explanatory variable and their response variable mixed up, because in a lot of problems where you're going to be doing this by hand, you have to identify which is going to be your explanatory variable and then which is going to be your response. And if you get them backwards, then everything's going to be off because you're going to do everything upside down. But we can assume that the femur in this case is going to explain the humerus bone. And so if I plug in my values, so I'm going to write this out obviously using the rounded values. My correlation coefficient we said was 0.994. When I multiply that by my standard deviation in y, that's 15.89. And I want to divide by the standard deviation of x, which I said was 13.198. Okay, let me show you what happens if I just use my rounded values. So if I just take 0.994 times my standard deviation in y, which we said was 15.89, and divide by 13.189. Okay, the value I get is 1.1975. if I use the actual values that I've stored, so I've retained all of my decimal places, then I'm actually going to be dealing with my alpha keys. And so if I, instead of having to hit second alpha before every single letter, if you hit the second button and then the alpha button, it'll lock. So then you can just use your alpha keys. So essentially what I want to do is multiply my correlation coefficient, which I stored in letter E, and I want to multiply that times the standard deviation of y, which I stored in letter D, and I want to divide that, oopsie, I guess I have to change that to division, or times, I mean, times D, and then I want to divide that by the standard deviation in x, which I stored in letter B. There we go. So it's going to be E times D divided by B. And when I do that, notice the values are slightly different. I mean, when you're rounding to 3 decimal places, it's just slightly different. But if I round with the slope, then obviously when I calculate the y-intercept, it's going to also be off. And then any prediction I make based on those rounded values is going to be even further and further off. So I'm going to go ahead and write my slope is 1.197. And then to calculate my y-intercept, remember we said it's going to be y bar minus the slope times x bar. Well, the mean of y is 66. And I'm going to subtract my slope, which we said is 1.197, times the mean of x, which we said is 58.2. Okay, and again, if I use the rounded values, it's going to be a little bit further off. So I'm going to keep the value that is in my calculator right now, and I'm going to use it in the next calculation. So I don't need to worry about my alpha keys when I'm typing in 66. I can. It's not letting me. All right, and then I want to do minus. And instead of typing in a rounded value, I'm going to use second answer times the mean. Sorry, my calculator is not letting me touch it, which is 58.2. Okay, and so when I press enter, I get a y-intercept of negative 3. Let's say that's going to round to 66. Okay, and so according to my values, the regression equation that I would get by hand is going to be y equals 1.197x minus 3.66. Now, one of the things you're asked to do is to interpret what the slope and the y-intercept represent. So remember, our slope is basically the predicted change in y as x increases by 1. So if I were to just replace that with my actual slope, it means that I expect the humerus bone to increase by 1.197 centimeters for every centimeter increase in the femur bone. That's how I would write it. So I would expect, so we predict, let me write this. So the slope, sorry, I don't have a ton of space. So the slope means we predict the humerus to increase 1.197 centimeters. I believe they're measured in centimeters from the last, I think from the last class we used centimeters. For every 1 centimeter increase in the femur. Okay, that's what the slope represents. The y-intercept then would be the length of the humerus, or the predicted length of the humerus, for a femur that is 0 centimeters, which doesn't make any sense in this problem. And that's actually going to happen quite a bit. When you're looking at your y-intercept, it's not unusual for the y-intercept to be nonsense. And we'll talk about that in just a little bit, why sometimes it doesn't make any sense. But our y-intercept is basically going to be the predicted length of the humerus is negative 3.66 centimeters when the femur is 0 centimeters. And obviously, you're not going to have a bone that's 0 centimeters long. I mean, the whole thing with the y-intercept is nonsense. Okay. I also want to show you how to calculate the linear regression equation using your calculator. And obviously, if you have data, you're going to let the calculator do the work. But it is important, if I just give you the summary statistics, that you can also come up with the equation of the line. So using the calculator, and this is what you're going to be doing any other time you have data, you're going to go to Stat and scoot over to Calc. And then there are actually two equations that you can use to, or two commands that you can use to come up with a linear regression equation. You can use option 4, and notice that the form of the equation is ax plus b, so the value of a is your slope and the value of b is your y-intercept, which contradicts the formula on our paper. So that's why I said don't get hung up in the a and the b. Just remember that the coefficient of x is always your slope. Option 8 is another form of the linear regression equation, and this time this matches what our book uses, which is a plus bx. So it doesn't matter which one you use. I usually, after you've identified the x values and the y values in the appropriate lists, I like to store the equation in y equals. So when you get to the store regression equation, if you hit the vars button, I basically want to store it in y equals, so I'm going to go to a y variable, y equals, those are all functions, and then I can select the equation where I want to paste it. And so if I press enter, that gives me the equation of my line. And let's take a look at the value of a and b. So we said in this form of the equation, b is my slope. So does that match what I have on my paper? Is 1.1969, is that the same thing I got? Yeah. And if I look at the y-intercept on the calculator, it's negative 3.69, or I'm sorry, 6595. And again, that just rounds to negative 3.66. So as long as you're not using the rounding values or the rounded values, they should be the same. So if you didn't use rounded values. Okay, obviously if you use the shortcut, and there is a shortcut, actually let me show you. If you very quickly wanted to come up with the slope and the y-intercept, there is a shortcut for finding the mean and standard deviation when you have two variables. And I'm going to show you this, although I don't recommend that you use it. So we're used to using, if you go to Stat Calc, we're used to looking at the one variable statistics. Well, you can also calculate, if you have two variables, you can actually calculate the summary statistics from two lists. If you just select list 1 and list 2 and then go to calculate, notice that our x bar is given at the top. That's 58.2. And remember, we want to choose S sub x as our standard deviation, which is 13.198. Notice if you scroll down, it gives you the same thing for your y variable. So it'll tell you the mean of y is 66, and the standard deviation, again, we want to use S sub y, is 15.89. So that would be a very fast way of calculating your summary statistics. But again, there's no way to store the mean and the standard deviation to keep your decimal places. But if you're just trying to get this done quickly, that would be the fastest way to come up with your summary statistics. Once you have a equation, then we can actually use the equation to make predictions. And like I said, that's the whole point of modeling. Okay, so the last step in this problem then is to make a prediction. If we know that a sixth specimen was found and we know that the femur of this beast, whatever it is called, was 70 centimeters long. Well, I know that the femur is an x value, so I'm essentially trying to make a prediction if I know that x equals 70. So I essentially just want to plug the 70 into my equation, and there are lots of different ways that we can do this. You can look at your table. If you hit second graph, that'll bring you to a table, and you can enter the 70 in. Now I'm able to do that here because my table is set to ask. If it's set to auto, then you have to scroll back and forth. The other thing you can do is if you have your graph, I think I turned my scatter plot off. Let me turn my scatter plot back on. Let's try that. Whoops. Oh, you know what? I adjusted my, shoot. You can also do it from the graph. Obviously, I changed my window settings and that's not possible. But another way, as long as your equation is in y equals, so if I go to my y equals, I can see that my equation is still in there. I can actually use function notation on my home screen, and this is another way that you can calculate or predict a value for y for a given x value. If you go to your vars button and go to y-vars, you can actually pull up the function. So I saved my equation in y1. I can actually pull that up. And then this is just a function. So if I put the 70 in parentheses, this is like f of x to the calculator. It's like me plugging in a value for x into my function. It's just function notation, and I can do that with any value of x, and my calculator will give me the corresponding value of y. And remember that this is just a prediction. So the regression model that I have predicts a humerus of 80.123. So I'm going to actually put a y hat there, 80.123 centimeters. Would be the length that it would be predicted for a femur bone of 70 centimeters. And this is a reasonable prediction. Given the fact that my model is good, the correlation coefficient was 0.994, so that's a good model. I knew from the scatter plot that it was a strong linear association. And the value of 70 is within the range of my data values. And so it's reasonable. It fits in with the rest of the pattern of the data. That would be a very good estimate, a good prediction, and I would be confident in it. But let's talk about predictions. We do need to be careful when making some predictions. For example, what is called extrapolation. If I have a regression model, it's only good for the data that I have. So in terms of like the support for the model is only good for the domain values that I have for X. Beyond that, I have to be very careful making predictions. So extrapolation is what we call the use of the regression line for predictions that are far outside the interval of values of the explanatory variable. So if it's outside the domain of the data that I have, then I want to be careful when I make predictions. Algebraically, you can still do it. I mean, certainly you can plug in any value in for your equation and get a corresponding value for y. But how much confidence you have in that estimate is going to be determined by how far away the x value is from the rest of your data. Because we don't know what happens beyond the domain of values that we have. So our model is only supported by the data that we have. Any predictions made that are too far away may be inaccurate. And there's really no way to tell if we don't have the data to support it. And you also noticed, I think even in the last equation, that the y-intercept didn't make any sense. And that's because, again, when x equals 0, we're extrapolating. If my data, if we go back to our femur example, my data on the femurs went from 38 centimeters to 74 centimeters. So if I'm to go back to 0, that's considered extrapolating. And notice that my y-intercept was nonsense. I mean, that doesn't make any sense to have a humerus bone that's a length of negative 3.66 centimeters. So often that happens. And so that's something that you'll want to comment on anytime you're interpreting your slope and your y-intercept. So again, just to reiterate, you don't want to make predictions using values of x that are much larger or much smaller than those that actually appear in your data. So it isn't unusual for your y-intercept to be negative and for it not to mean anything with respect to the problem. And so that would just be something that you'd want to comment that we're extrapolating for our y-intercept, and that's why it doesn't make any sense. The only other thing I wanted to point out with respect to using your calculator for calculating the linear regression equation, and again, I don't have the, I had to pause and I put different data into my calculator. But in order to get the correlation coefficient to come up when you're doing linear regression, I have data in here. I'm going to go ahead and just show you what happens. If I do linear regression here, I'll use option 4, and I'll just go ahead and use the data that's currently in my list 1 and list 2. When I press enter, it just gives me my slope and y-intercept. The calculator will calculate the correlation coefficient for you. There's no separate command, unfortunately, like there is with standard deviation or mean. But the calculator, if you're doing regression, will report the correlation coefficient. But you have to turn the diagnostics on. And the way you do that is if you go to your second catalog, which is second 0, you can either scroll all the way down until you get to the D's, or you can just type in the letter D and it'll automatically move you to the D section of the this is basically your index for the calculator of every single command there is. Notice with the A in the corner on the top right corner that it's already in alpha mode. So if I hit the letter D, it'll take me down to the D's. And what I want to do is scroll down until I see something that says diagnostics on. And so I'm going to press enter, and I'm going to press enter one more time until it tells me that it's done. Now if I go back, if I hit second enter, and do my regression command again, when it reports my slope and y-intercept, it'll also report an r-squared value and an r value. The r value is the correlation coefficient, and again, I have different data in the calculator at this point. That's why the r value is 0. The r-squared value we will define another time. So you have several more examples to do in class, problem number 2 and 3. And with number 3, you can use your calculator. You do not have to come up with a regression equation by hand. But I do have another example to give you a little bit of practice with calculating it by hand, and it's in a wrap-up. So it's a separate worksheet that I'd like you to do. So I'd like you to work together on these exercises. Your homework is also, you can begin that once you're finished with the classwork. Use your classwork, use your notes to help you with the homework. And I'm going to post this video to Blackboard and to YouTube. So if you need to review it to get through your homework, please feel free to do so.